All right, here we are. The density of pulsars. Neutron stars. Neutron stars are pulsars. And here you see a spoonful of a neutron star, which would be incredibly heavy. So that spoon would have to be incredibly massive to hold it, um, because a neutron star, which you're seeing in the picture here, a spoonful of this would weigh more than Mount Everest. That's how dense pulsars are. And we'll talk about pulsars. So let's write it over here, right? A spoonful, which you see here, a single spoonful. A single spoonful of sugar, right? Single spoonful, or a teaspoon, right? A single teaspoon, right? That is a teaspoon, like tea over here. Single spoon or teaspoon of a neutron star, which is a pulsar, neutron star, would have a mass. By the way, there's other problems with this too, which I'll talk about in the video. Would have a mouse would have a mass of about 1 billion tons. 1 billion tons, which is Mount Everest, right? A little heavier than Mount Everest. And they're named neutron stars, by the way, these pulsars, because they're composed of neutrons. Seems obvious. And what happened is the protons and the electrons in these atoms have formed neutrons under incredible dense conditions. And we'll talk about that. Now, if you want to compare something, let's say we took a tablespoon of our own sun and we scooped up, let's say hypothetically we can scoop up a tablespoon of our own sun. A tablespoon of our own sun will only weigh 5 pounds, right? But a tablespoon of this neutron star, like I said before, it would weigh 1 billion tons. Completely different. The density is amazing on these neutron stars. And here we have the size of a neutron star. So neutron stars are small. They're small in cities. If you think about, let's get my pen here working. So if we think about the size of Brooklyn here, down here, right? Here's Brooklyn. And this map is not so accurate, but Brooklyn could be 8 miles long, 8 miles wide. It could have a radius of 8 miles wide. And let's say from Nassau County right over here, Long Island, all the way to Manhattan, that could be about 26 miles. Neutron stars usually have a radius about close to 6 to 8 miles. So we're looking at a radius here of 6 to 8 miles. That's the radius of a neutron star. They're a size of a city. Imagine that in space. But they're incredibly dense. So obviously you couldn't put a neutron star on Earth because the Earth would be crushed from the gravity. So if a neutron star was placed in our solar system, the size of this small city, everything would rotate. Everything will revolve around the neutron star, even the sun. So neutron stars, they may be small, but they have an incredible amount of gravity. And they're incredibly hot. So if you think of the surface area of our sun, so we'll think right over here, the surface, not the surface area, the surface temperature of the sun, put the sun here, that's about 5,500 degrees Celsius. Now, if you take the surface area of a typical neutron star, pulsar, surface temp, well, it could be over 1 million degrees Celsius. Right? So much, much hotter and much, much denser. And if we go back to a spoonful of the neutron star, we couldn't put that on Earth either. Because what would happen, the gravity, right now, gravity is holding together a neutron star. And the gravity is extremely strong. It's compressing the neutrons into a very, very small space, in this case, the size of a city. there's an incredible amount of pressure in a neutron star. So if you somehow were able to bring a spoonful of a neutron star to Earth, it would release that pressure, causing an immense explosion. So we can't even bring that to Earth in itself. And again, here's a neutron star, and they're called pulsars because they're pulsating. They're shooting out these enormous amounts of energy. And neutron stars were once, some people might call them failed black holes, in a sense, just to joke around, because they were once massive stars, bigger than the sun, 10 times bigger than the sun. And of course, they ran out of fuel, which most stars will, and our star will also run out of fuel. And they started collapsing under gravity. And as they started collapsing, the protons and neutrons fused together to create neutrons. And the only thing that's keeping the neutrons from collapsing further, and I'll write this down, it's called neutron degeneracy pressure. Fancy word. I'm going to put it down if I can find my pen. Let's see. Let's use red over here. So it's called neutron degeneracy pressure. It's keeping the neutron star as a neutron star. In other words, basically what this is saying is that two neutrons can't be in the same place at the same time. They cannot occupy the same quantum state. It gets a little fancy here. It's because of this principle called the Pauli exclusion principle, which I won't get into here, but that's basically two neutrons can't be in the same place. So because of this neutron degeneracy pressure, the neutron star stays a neutron star. However, if there was another neutron star within the area and they merge together, then you can get a black hole. So if there's enough mass, a star can become a black hole. If there's not enough mass, but almost enough mass, it could become a neutron star, which is a pulsar. And that's really being oversimplified. And by the way, astronomers have observed many binary systems having two stars where neutron stars do merge, and what happens is there is a formation of a black hole as a result. So here's a picture. There's the Earth, and there's a neutron star, probably even smaller than that. Then you see a white dwarf, which our sun will eventually become because it's a yellow dwarf now, and it's not massive enough to become a neutron star. But if a neutron star, it's very small, it's as big as a city, has enormous amount of gravity, and so everything in our solar system would orbit it. And it's extremely hot. It's hotter than the sun. So our temperature, if somehow it appeared where the sun appeared, even Earth would be hotter than it is. So it's much hotter than the sun, much smaller than the sun, but much more gravity than the sun, neutron stars. So, and here's something, pulsars are neutron stars. But here it is. Not all neutron stars are pulsars, but all pulsars are neutron stars. So the pulsars, neutron stars, they're very dense, like we said in this video, extremely dense, extreme strong gravity, extremely hot. But a pulsar, which is a neutron star, is also emitting radiation from the poles. It has a strong magnetic field, very strong magnetic field. And they rotate very rapidly. They're just rotating and shooting out these jets of radiation. That's what a pulsar does. So again, not all neutron stars are doing that. They're not all shooting out radiation from the poles. And if they are, they're pulsars. But again, all pulsars are neutron stars. So if we go back to our picture in the beginning, here's our picture in the beginning. Again, a spoonful of a neutron star, which we wouldn't be able to put on Earth. It'll weigh as much as Mount Everest, and it would still be extremely hot, so you don't want to go near it. In fact, its gravity will be strong enough to push you in and crush you. All right, that's the density of pulsars today.